Anna McLaughlin. I'm a senior statistical scientist at Berry Consultants, and in this video I'll be talking about how we monitor clinical trials for futility. So we can define futility as the inability of a trial to reach its stated objectives. During the course of a clinical trial, it may become apparent that the trial is unlikely to reach its objectives, and we may wish to stop the trial early before it reaches completion. And this may happen for unforeseen operational issues, such as difficulty accruing patients. But what I want to talk about is futility rules that we pre-specify as part of our design and that are based on data on the primary endpoint. So why might we consider futility? We have many research questions, but we always have limited resources available to answer them. So futility rules are one of the tools we can have in our toolbox to help efficiently allocate our resources. The goals of a futility rule, first of all, we want to limit the exposure of subjects to a treatment that they're unlikely to benefit from. And by saving patient resources, by stopping a trial that's unlikely to win, we can then better allocate those resources to more promising pathways. But we want to also be careful to not be too aggressive, and we want to avoid stopping trials that might otherwise go on to win. So let me put this in a concrete example. Suppose that we're designing a trial comparing a new treatment to a control treatment, and our primary endpoint is a responder rate. We'd like to design the trial to have 80% power to detect a difference of a 35% responder rate on control versus a 55% responder rate on the treatment. So it's a 20% absolute improvement. With a one-sided type 1 error rate of 2.5%, our sample size calculator tells us that we need 192 subjects, or 96 per arm. So at the end of the trial, we will declare the trial to be successful if the p-value is less than 2.5%. And in order for that to happen, we need to observe a 15% improvement of the treatment arm relative to control. So now suppose that we're 2/3 of the way through our trial. So we have 128 total subjects, and we observe the following data. So out of the 64 control subjects, we have 21 responders, and that gives us about a 33% response rate. And on the treatment arm, we have 39% response rate. So our observed difference between treatment and control is 6.3%. Now, what do we think about this? 6.3%, it's not terrible. It's at least not going in the wrong direction. But 6% is considerably smaller than that 20% that we anticipated at the start of the trial. And it's much lower than that 15% that we're going to need to win at the end of the trial. So is it possible for us to still win this trial? With that 6% effect that we already have in the bank, and only 1/3 of the trial left to go, we would need to see a pretty remarkable turnaround in order to reach that 15% by the end of the trial. In fact, in our remaining 64 subjects, we would need about a 33% effect. And our intuition probably tells us that that's unlikely to happen given what we've seen so far. So let me try to put this in the context of a sports example. Suppose that you're watching a football game and your favorite team is down and it's at the end of the 3rd quarter. So the game's not over yet, there's still 1 quarter left to play, but how likely is it that your team can come back and win the game? The way that we answer that question statistically is by predictive probabilities, which directly measure the likelihood of winning the end of the trial. And predictive probabilities incorporate various sources of uncertainty, such as uncertainty in how the future subjects are going to behave, as well as uncertainty in our current estimates of the parameters. So just because we've seen a 6% effect right now, doesn't mean we're going to see exactly a 6% effect in the remaining subjects. There's some variability to be expected there. Going back to our example, if we calculate the predicted probability of eventual success, it's only about 6%, so not very likely. So now let's go back and rewind the clock to when we designed the trial, and suppose that we're going to add in a pre-specified futility rule after 128 subjects. And we'd like to stop the trial for futility if the predictive probability is too small. So how do we go about choosing the right threshold here? Well, it's going to be about finding a balance. So what we would ideally like to do is identify those trials that are unlikely to win at the final analysis and terminate those trials early. But we also want to be careful not to be too aggressive and mistakenly stop those trials that would go on to be successful. So our intuition should tell us that if we have a high threshold for our predictive probability, then we'll be more likely to stop trials early for futility, which is a good thing. We can stop more trials that are unsuccessful, but we may also make more mistakes. If we set a lower threshold, we'll make fewer of those mistakes, but we kind of defeat the purpose and we may not be able to stop as many trials that should stop. No rule here is going to be perfect, so it's going to be about finding that appropriate balance and taking into consideration input from the various stakeholders. So one way that we can evaluate how well our rule behaves is with clinical trial simulation. So what I've done is I've told the computer to randomly generate data for a trial that has an interim analysis at 128 subjects and a final analysis at 192. Right now, I don't have a rule in place to stop for futility, but I'm just going to show you what the data looks like at the interim and at the final analysis. On the graph, each one of these dots represents one simulated trial. On the x-axis, I'm showing you what the treatment effect is at the interim. So it's the difference between the responder rate on treatment versus control. And the y-axis is that difference at the final analysis. And the dots are color-coded according to whether or not they meet our success rule at the end of the trial. So the green dots are trials that had a p-value less than 2.5%. Those are trials that win. And the black dots are trials that do not win. And we see there's a pretty clear distinguishing line between the successful and unsuccessful dots, and that happens at about a 15% response rate. Now these trials that I simulated, I generated the data from various assumptions about what the true underlying effect is. So now what I've done is added a plot where I summarize those dots according to the underlying truth. So the height of each one of those green bars represents the proportion of trials that are successful under that scenario. So for example, if the truth is a 20% absolute improvement, the height of that green bar is 80%, and that's the power of our trial. The far left bar, that's a scenario where there's truly no treatment effect, and this is the null scenario. The height of that green bar is 2.5%, which represents our type 1 error rate. The table on the right side of the screen is just the same information, but it's in numeric values. So now what I'm going to do is introduce a futility rule that says we will stop the trial at the interim if the predictive probability is less than 1%. So notice that some of the dots have now changed color. Some of the dots that used to be black have now turned blue. And this represents trials that would have been unsuccessful at the final analysis that we've now terminated for futility at the interim. And this is a good thing. So for example, in our null scenario, we see that the blue proportion of dots is about 60%. So we've been able to stop 60% of the trials early. So 60% of those trials stop at a sample size of 128. The remaining 40% of those trials go out to a sample size of 192. So on average, we've reduced our sample size to about 153 subjects. Notice that we've also stopped some trials for futility in our good scenarios, but that's not necessarily a bad thing if we're stopping trials that were already doomed to failure. But notice that we have made a few mistakes, so some of those green dots have now turned to pink. That represents trials that would have been successful at the final analysis that we've now terminated early. But that doesn't happen very often here. It's less than 1% of our trials. As we start to increase our futility threshold to 5%, 10%, 20%, or even 50%, you can see how the height of those bars changes. So as we increase that threshold, we start to stop more of our unsuccessful trials early. That is, we're turning more of the black dots to blue, but we are also making more mistakes and turning some of those green dots to pink. So in this slide, where we have a futility threshold of 50%, one of the things we can notice is how this affects our power. So remember that our scenario of a 20% absolute improvement had 80% power when we had no futility rule. Now, with this high threshold, that power has decreased to about 69%. So we've been terminating trials early that we shouldn't have, and that loss in power directly corresponds to that pink area in our bar. We also see that we decrease our type 1 error rate. In the null scenario, our type 1 error went from 2.5%, now it's down to about 1.7%. It's all about finding the right balance. So with a high threshold, we can stop more of our trials early, we can save more of our patient resources, but that comes with the risk of a decrease in our power. So predictive probabilities aren't the only way that we can make futility decisions. There are also frequentist methods like group sequential boundaries based on p-values or conditional power. And there are some other bells and whistles that I'm not going to talk about here. So our example just had a single interim analysis, but we could also consider having multiple interims to look at futility. And when we do that, that'll come with some additional choices, such as how early do we look, how often do we look. And again, looking at simulations can help us to make those right choices. Also, if we have a study that has multiple treatment arms, we may wish to construct futility rules for each arm individually, as well as for the overall trial. So there are lots of different ways we can do this. An important consideration whenever we take interim looks at our data is to ask whether or not we increase the probability of making a type 1 error rate. Well, as we saw in our graphs earlier, the futility rule actually decreases the type 1 error rate. So there's no statistical penalty that we need to take for having futility interims. But we also saw that there's a risk of decreasing power. So we always recommend that futility rules be pre-specified as part of the design. So even when a trial has a data monitoring committee that's tasked with monitoring the safety and the integrity of the trial, it's a good idea to write down a futility rule that lays out the expectations for how a trial would be stopped for futility. And remember also that it's the trial that's futile. It's not necessarily the treatment. So for example, it could be that the treatment effect is just smaller than what we anticipated and the trial is underpowered to detect it. And all that futility tells us is that collecting additional data is unlikely to result in a statistically significant outcome. So in conclusion, there's no one-size-fits-all futility threshold. And the choice of how to choose that threshold depends on things like the nature of the disease, the availability of other therapies, and perhaps other financial considerations as well.